arc length equals radius times 65. The math looks completely fine, right? Well, actually, no. This one tiny calculator mistake, forgetting to check if your calculator is in degrees or radians, is the #1 reason candidates just bleed massive marks in the Cambridge IGCSE Additional Mathematics 0606 exam. You could do all the algebra perfectly, but if your calculator mode is wrong, you lose the grade. Today, we are going to fix that permanently.
And hey, circular measure isn't just some abstract textbook concept designed to torture you. Take the Singapore Flyer, for example. It's a massive structure with a 75-meter radius, taking 30 minutes to complete a single rotation at a constant speed. To figure out exactly how fast those passenger capsules are traveling through the air, engineers rely on the exact same circular measure principles you're about to master. This is fundamental real-world mathematics.
Here is our exact roadmap to unlock top-band exam mastery today. 1. The radian trap. 2. High-mark strategy framework. 3. Sector, area, and perimeter tools. 4. Tackling past paper questions. And 5. The final exam challenge.
Okay, let's dive right into Section 1, the radian trap.
You know, standard textbook revision completely fails here when you actually sit down in the exam hall. Let's look at the most common and frankly most painful mistake examiners report seeing year after year. But before we can spot the trap, we need a firm foundation. What actually is a radian? Well, radian measure is used all the time in advanced mathematics because it just simplifies calculations immensely. Simply put, 1 radian is the angle created in a sector when the arc length is exactly equal to the radius of the circle. And since the circumference of a full circle is 2 pi times the radius, that means there are exactly 2 pi radians in a full 360-degree revolution. To put that into perspective, 1 radian is roughly 57.3 degrees.
So look at this flawed student answer. They see an angle of 65 degrees, they see the radian formula for arc length, which is r times theta, and they just multiply the radius by 65. 0 marks. The formula arc length equals r theta only works if theta is actually in radians. Now compare that to the top band calculation. This student either converted 65 degrees to radians first by multiplying by pi over 180, or they just used the standard degree formula. The stakes of ignoring your calculator's DRG button, degrees, radians, gradients, are incredibly high. Literally always verify your calculator mode before you punch in a single number.
Moving on to Section 2, the high-mark strategy framework.
In just a moment, I'm going to show you the exact examiner clue hidden in the 0606 exam questions that completely changes your calculation path. But first, you absolutely need this foolproof 5-step strategy framework that makes that clue completely obvious to spot. Step 1, read carefully. Circle those command words. Step 2, select your method. Does the question give you an angle in degrees or as a fraction of pi? Because that dictates whether you use the degree toolkit or the radian toolkit. Step 3, show your steps. No magic numbers appearing out of thin air. Step 4, check accuracy. Seriously, are you in the right calculator mode? And Step 5, state your final answer clearly, usually to 3 significant figures unless stated otherwise.
All right, Section 3, sector, area, and perimeter. Now, what's really interesting here is how much cleaner that radian side is. Look at the formulas. For degrees, the arc length is theta divided by 360 times 2 pi r. The area is theta over 360 times pi r squared. It's kind of bulky, right? But check out the radian formulas. Arc length is simply r times theta. Sector area is just 1/2 r squared at theta. Because a radian is mathematically linked to the radius itself, the formulas just strip away all those fractions and pi symbols. It's elegant, it's fast, and let's be honest, in a timed exam, speed is an absolute weapon.
Let's apply our framework to a direct question to build some momentum. We have a sector of a circle. The radius is 8 centimeters. The area is 25 square centimeters. The command here is to work out the angle at the center, and specifically in degrees.
Since our target is degrees, we select our degree formula for area. Area equals theta over 360 times pi times r squared. We substitute what we know. 25 equals theta over 360 times pi times 8 squared. Now we show our algebraic steps. Multiply both sides by 360, divide by 64 pi. Punch that into the calculator, making absolutely sure it's in degree mode, and we get 44.76, which we round to 44.8 degrees to 3 significant figures. Boom! Framework executed perfectly.
Let's turn up the heat. Section 4, tackling past paper questions. It is time to jump into the trenches of Cambridge past papers. This is where multi-step questions separate the top band students from the rest. Take a look at this classic setup from a June 2014 paper. We have a circle, center O, radius 8 centimeters. There's a chord PQ that is 12 centimeters long. The angle POQ is given as theta radians. The exam command is, show that theta equals 1.696, correct to 3 decimal places. So the absolutely crucial point here is that phrase, show that. This means you cannot just plug in 1.696 and work backward. No way! You have to derive it from scratch to get those reasoning marks.
So how do we actually crack this? Well, step 1, look at triangle POQ. Because OP and OQ are both radii of 8 centimeters, it's an isosceles triangle. You can drop a perpendicular line to split it into 2 right-angled triangles, or you can deploy the cosine rule. Step 2, calculate the angle. If you split it, you'd use sine of half theta equals 6/8. Step 3, crucially, your calculator must be in radian mode here, because the question literally specifies theta is in radians. Step 4, write down your unrounded answer first, something like 1.6961, and then clearly state it as 1.696 to exactly 3 decimal places as requested. Now, once you have that angle, past papers will almost always ask you for the area of the shaded segment, that little slice between the chord and the arc. Here is your bulletproof strategy. First, calculate the total sector area using 0.5 times r squared times theta. Second, calculate the area of the triangle inside it. The fastest way is using that trigonometry formula, 0.5 times a times b times sine of angle C. Since a and b are both the radius, this just becomes 0.5 times r squared times sine theta. Finally, just subtract the triangle from the sector. It works every single time.
And that brings us to Section 5, the final exam challenge.
Okay, you have the formulas, you have the framework. You know exactly how to handle show that commands. Now it's time to put it all together and test your spatial reasoning. Here's the tricky scenario from the source exercises. We're looking at the cross-section of a paperweight. It's a sphere with a radius of 5 centimeters, but the bottom is cut off to create a flat, circular base with a diameter of 8 centimeters. The question asks, calculate the obtuse angle at the center in radians. Take a second and really think about it. How do you map a 3D description into a 2D geometry problem? Where exactly does that triangle go?
And this brilliantly illustrates the secret to these high-tier questions, drawing your own clear diagrams. From the center of the sphere to the edge of the flat base is the radius, 5 centimeters. The full flat base is 8 centimeters, so half of it is 4. If you drop a line straight down from the center, you create a right-angled triangle. We want the angle at the center, so sine of the half angle equals opposite over hypotenuse, 4/5. The inverse sine of 4/5 in radian mode gives a half angle of 0.9273 radians. Multiply that by 2, and the total obtuse angle is 1.85 radians.
Before we wrap this up, I really need to burn this examiner strategy into your mind. Sometimes a question will ask for the exact area of a shaded segment. The moment you see that word exact, put your decimal point away. To secure full marks on these exact area questions, you must leave your answer in terms of pi, or as surds and exact fractions. If you round early, you immediately drop out of the top mark band.
So you've just mastered the circular measure strategy, and you know exactly how to avoid the radian trap. But there is a massive piece of the puzzle still missing. You could know all the math in the world, but if you misinterpret a Cambridge command word, your grade is capped before you even write a single number. In our next explainer, we expose the exact command words that dictate your mark band and show you how to decode them instantly. You do not want to walk into your exam without this knowledge. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Select the next explainer on your screen right now to decode those hidden command words, and I'll see you over there.